Today we begin looking at sedimentary rocks and processes. Sedimentary rocks form under very specific conditions and environments. We must consider the rock cycle, that sedimentary rocks are simply just a part. They're in the cycle itself. That if we have an igneous rock, it can be broken down into sediment. We could have a metamorphic rock, it could be broken down into sediment. We can even have a pre-existing sedimentary rock that's broken down into sediment that then gets, as it's broken down, it gets transported, it gets relocated as deposition, and it gets compacted, cemented together. So sedimentary rocks are just a part, a step of the process of the rock cycle. Sediment, or detritus, is transported by wind, water, or ice, where it gets deposited. It must then be compacted and cemented into solid rock. When we look at wind, water, and ice, there are certain terms that are associated. Wind are called aeolian processes, water are fluvial, and ice is glacial processes. Well, what is sediment? Well, sediment is a naturally occurring material broken down by processes of weathering and erosion, and it is subsequently transported by the action of wind, water, or ice, and by the force of gravity acting on the particles in transport. More often than not, we're going to be looking at water. Water is the most common transport vehicle. For example, sand and silt can be carried in suspension in river water, right? The particles are suspended in water. We called this turbidity once upon a time ago. And they're suspended in the water itself, and on reaching the sea, be deposited by sedimentation, and if buried, they eventually can become sandstone and siltstone. These are sedimentary rocks. So as the energy changes from moving, right, so you have to have kinetic energy that's going to suspend it, be able to suspend the particles. Over time, eventually the sediment's going to settle out. So we find this at specific locations, but the settling occurs that all of these were suspended, they eventually settle out. So this is the material that we're looking at. Detrital sedimentary rocks form in basins. They're found where water flows into either oceans or lakes or other low areas by the following process. Weathering mechanically breaks down a rock, right, from a parent rock, creating smaller and angular fragments. Erosion transports the rock fragments to a lower energy level, right? Water flows downhill. It's going to transport whatever it can carry. Sediment is deposited, right, after its transport. The sediment is compacted by pressure over time, right? The weight from the above sediment, so the sediment's overlying it. And the sediment is cemented together by cementing minerals. These are the 5 steps that lead to the formation of detrital sedimentary rocks. So let's watch this video here. Now I want to focus on something here. Let it load.
This animation shows a side view of an area where a river flows into a lake, or any other body of water for that matter. As flowing water enters the body of water, its velocity decreases. The water's ability to carry sediments also decreases. You can watch this animation. You'll notice that stream flow slows down, right? The velocity is slowing down. So as it's slowing, larger sediment cannot be carried, so it's dumped out first. This is where sand grains then follow that. So we get large particles, what we call coarse, to sand grains into clay size. And this is called gradation, or this is a sequence of sediment from larger or coarser to smaller that we'll call fine.
So rock fragments, they range in size. We'll call this from coarse to fine, and that's what I was emphasizing on the little video. Coarse we call, well, boulders, there aren't pictures of boulders on here. Boulders are just simply a particular size here. And we're not going to put a number to it just yet. You just need to realize that boulders here are just larger rocks. But we do call pebbles. Pebbles imply a certain size here. And we get into gravel. We can talk sand. Sand is just smaller than pebbles and gravel. But you can have coarse sand, you can have medium sand, you can have fine sand. Right? It's all based on the sizes of them. You can have fine sediment that we call silt, right? What we refer to as mud. And you can have very fine muds that we call clay. So we have a sequence here from large to small that we call coarse and fine. We have to look at what a delta is. A delta is where we find deposition from the mouth of a river. A delta is a landform that is created by the transport of sediment to oceans. And we see that water is flowing from right to left here. And we create this landform. This is the delta. It's contained here. That all of this was sediment that's been transported through this body of water, through this river here. And notice that we still have rivers that are kind of moving through here. It's kind of a semi-dendritic river system here. But you just have conduits. These are allowing for water to flow, but it's still building. This delta is growing here. And we can see it in this picture here. Water's flowing from land to sea level, right? It's flowing downhill, it's transporting the sediment. And the sediment is building. Here's the delta. The delta here is actually kind of internal. Here's a picture of kind of a steeper slope from a mountain directly to a body of water. And this would be another picture of a delta. And then here's another picture just illustrating that sediment is carried in the water. So I'm just trying to emphasize that water is doing a lot of transport of sediment. The deltas are the result of rocks and land being broken down and transported. Where we find the mouth of the river, we find sediment being deposited. We find gradation of deposition that goes from coarse to medium to fine. You're going to find your largest particles where the river water slows the greatest. It's simply unable to carry larger particles. And then you get this gradation effect. You get coarser to sand grains and then into finer sediment. You can see the fine sediment here leading to a very high turbidity. Well, this occurs because of the velocity of the water decreases, thus decreasing the water's kinetic energy and capability to transport the sediment. If the water cannot carry it, it settles out in a specific order that we call gradation. So rock fragments, they tell their environment. Well, where do we find pebbles in this case, pebbles in smaller sizes of particles? Well, the largest materials that you're going to find are going to be found where we find water changing velocity, and these are going to be found at deltas. So as we go from our pebbles to our gravels to our sands, this is the gradation sequence. We're actually going to find these particles being closest or nearest the shore, and we get this gradation of sand grains even that get separated as the kinetic energy of the water changes. So we're still finding these in deltas. We find sand, obviously, where we find beaches. They get distributed by waves and, let's just say, ocean direction, movement. And we find the muds, they actually travel further from the shoreline because they're easier to travel. It doesn't take much kinetic energy. And they gradually are deposited in deep ocean basins. So we have to consider sorting and rounding. Sorting is the result here of how the energy in the water is able to organize them. Very well sorted are going to be, let's just say, homogeneous, or all about the same size. Where very poorly sorted, you're going to have kind of a heterogeneous grouping. You're going to have large and kind of medium and small materials together. So we'll focus on either poorly sorted or well sorted. So the sorting and rounding are the effects of the kinetic energy in moving water, or wind, acting to organize and or mechanically change the sediment. Here we can find something that is angular, right? It's kind of got the angled, it's got edges to it. Whereas here we'll say they're rounded, right? Some of them are spherical. This is going to be kind of still rounded, if you can see this here. It's just not a perfect circle. It's not spherical. Well, the rounding process takes place, as we've learned before. It takes place as there's action, there's transport along the stream bed itself. That this is a process called abrasion, and we learned this in the past, is a physical or mechanical process of rounding out angular particles during transport. So we can draw some conclusions from rounded particles. We know that they've been transported some distance, whereas angular particles have not been transported. They're generally located near their parent rock that they were broken from. So once we start having sediment that accumulates, we have to start looking at bedding planes. In geology, a bed is a small division of geologic formation, or stratigraphic rock series, marked by well-defined divisional planes, which we call bedding planes, separating it from layers above and below. So if I look at these layers in here, these are very defined bedding planes where you get subtle or slight changes in deposition, right? We just see it as the color differences, and that's what this is showing here. These are just different bedding planes. This could be a shale, this could be sandstone for that matter, just as a little different depositional bedding plane is showing us what we see here in the changes of deposition. So we started off looking at detrital sedimentary rocks. That's what we're looking at here. If they contain rounded particles, we call them conglomerates. And if they contain angular particles, they're what we're going to be calling breccia. They're both containing these gravels. They're particular sizes, so their texture is going to be coarse. They're going to have coarse here. They're actually a combination of coarse and fine, but we can visibly see rocks that are either rounded or angular within the rock itself. We can say medium. Medium could be your sands, your sandstones. We can see these very defined bedding planes here. And we have a pretty homogeneous grouping of sand grains themselves. When we start talking about mud, we're really going to be kind of lumping these together and call them shales. We're not going to differentiate. But just to say muds are going to form these very fine particulate rocks that we're calling shale or mudstones. So these are what we're looking at here, from fine to very fine sediment that accumulates to form these types of sedimentary rocks. Chemical sedimentary rocks are a little bit different. They generally form from some precipitate. They come out of solution. So the first ones we can look at, if we talk about crystalline limestone. Here's a picture of a crystalline limestone. It's going to be comprised of primarily calcite. So therefore, it'll effervesce vigorously in the presence of a weak acid of HCl. Here we have coquina. Coquina is a little different. Because it contains shells, it's actually categorized as a biochemical limestone, or in this case, a biochemical rock. It's a subgroup of chemical because it has evidence of kind of living organisms. These are the shells of past living organisms. We can also talk or look at fossiliferous limestone, if you see fossils here, right? Also, all of these are going to effervesce vigorously because they contain calcite. Moving on here, we can look here at chalk. Chalk is just microscopic shells in clay. Also, it's going to effervesce because it contains calcite. So this group right here, notice we have crystalline limestone. We're not going to do much with travertine, but we will do a lot with limestone, particularly crystalline limestone. All of these are comprised of calcite. Whereas this picture here is a picture of that of rock gypsum. It's just comprised of the mineral gypsum. It's a calcium sulfate in kind of essentially a part of two H2Os. So this is your formula. This is the composition of it. But this has the same components of gypsum, the mineral. This one here happens to be a chemical sedimentary rock. Here we can look at chert. Chert happens to be silica-based, right? Pure quartz. Is also going to have the characteristics of quartz. It's going to have a hardness of 7, according to the Mohs hardness scale. Here we have rock salt. Rock salt is also a precipitate. This is, generally speaking, it's crystalline, just made up of halite, the mineral halite. And lastly, we've got bituminous coal. Bituminous coal is kind of a tricky one. It's made from altered plant fragments or plant matter. That these can be, essentially, it was once living, but it's not in the bio realm. It's just simply kind of an organic rock. It's kind of weird. It fits a couple different titles altogether. All of those sedimentary rocks are formed in different depositional environments. Right? Beaches are going to have sand. So will sand dunes in, say, a desert. Where we find moving water, we're going to get different types of rocks formed. Where we find glaciers, so we're going to find different deposition. Right? Moving water in streams, etc. But when we start putting together rock strata together, this is an example of a stratigraphic profile. You've got different types of rocks in different sequences. But the question is a very unique one that I like to end this on. So herein lies the ultimate question. Does the sedimentary rock record that we record as strata, right, that we see as this rock stratigraphy, these horizontal layers of sediment deposited due to gravity, do they really tell Earth's story? We need to consider some ideas here. We need to consider how normal is average and how rare is rare. Which is more important, the magnitude of an event or the frequency in which it occurs? That the rock record of the Earth's history, right, the rock records history in many ways, but it also can be misleading and confusing. So we need to start thinking about, well, what is the rock record telling us? Metaphorically speaking, is the Earth's sedimentary record like a layered cake? Or is it more like Swiss cheese, meaning is it missing these gaps in time? Do breaks in the depositional record between layers represent more time than the layers themselves? So we've probably been taught the concept of uniformitarianism, that there's a great danger here, that uniformitarianism says that these slow, kind of mundane processes day to day are depositing sediment. But there's a great danger that we impose more order upon nature that actually exists. And that the Earth actually appears to have more of a semi-uniform, spasmodic, and episodic history. That we have these long periods of boredom, right? The uniformitarianism concept, yet these brief periods of terror, kind of this catastrophic scenario. That we have to consider the magnitude, right? How much energy is required to create this landform or deposit sediment? That the depositional sequences are significantly affected by the energy in the depositional media, the time in which the deposition takes place, and the quantity of how much sediment was in transport. That hopefully you realize that an asteroid impact is far more powerful than, say, that of just a yearly flood. And finally, we have to consider the frequency. How often do they occur? That rare low probability events have geologic importance. that 1 in a million becomes significant, that we could say it's going to happen definitely 5 times in 10 million years.